Welcome, ladies and gentlemen. May I have your attention, please? Thank you. Let's go ahead and get started with our graphing of our parent functions, y equals sine of x and y equals cosine of x. We first going to measure our axes, right? We want to go by 90-degree intervals here, so every tick mark will correspond to 90 degrees. And this way, my positive x-axis, we could go by 1, 2, 180 degrees, 270, 360 degrees. Extend that in the negative direction, so going by 90-degree intervals, 90, negative, 180 degrees, negative 360 degrees, and the same for our cosine function, 90, 180 degrees, 270, 360 degrees, and the negative direction as well, negative 90, negative 180 degrees, negative 360 degrees. Okay, ladies and gentlemen, last class, we developed our parent function, y equals sine of x, by considering our directed, right, vertical distance, vertical displacement above or below the origin after spinning that initial point, 1, 0, around our unit circle. And so if we don't spin any degrees, then we are 0 units above or below the origin. And so our key starting point for sine of x, when 0 degrees of rotation is corresponding to a y value of 0. So everybody, key point 0, 0 starts the sine function. Everybody make sure you have that. Now we oscillate back and forth between maximums, intercepts, minimums, intercepts, maximums, intercepts, and so on and so forth. So here we go, at 90 degrees, we're at a maximum vertical displacement. 180 degrees back to an intercept. 270 degrees is paired with -1, and 360 back to the x-axis. Extend the pattern in the negative direction as well. So at -90, we're at -1. Negative 180 is at 0, negative 270 at positive 1, and then back to an intercept. We're going to carefully connect that in a nice smooth sine wave. There should be no corners or kinks, right? Nice smooth roller coaster. You shouldn't have any corners like in an absolute value graph. We want nice, smooth, and well behaved. So here we go. Go ahead and raise your hand if you had the same parent function for y equals sine of x. Nice job. Y equals cosine of x is very similar, except for an important difference. Cosine measured the directed horizontal displacement from the origin. So after spinning 0 degrees, our initial point, 1, 0, was the full unit away from the origin. So it was at a maximum for my start value. So everybody, when we go and start our key point, our y-intercept value for cosine is 0, 1. Everybody plot that, please. So 0, 1 is our key start value for the cosine function. Now the behavior is the same, the cyclical behavior, where we oscillate back and forth between maximums and minimums, right? So x equals 90 degrees, we're down at the next intercept, 180, -1, 270, 0, 360, back to an intercept, negative 90 degrees, y equals 0, negative 180, -1, negative 270, 0, negative 360 degrees, back up to a maximum. All right, let's carefully connect those in a nice smooth sine wave. What? Yes, a cosine function is still called a sine wave or sinusoid, as you saw in the lesson master. There, they can be rewritten as sine or cosine. A horizontal translation would make any sine graph into a cosine graph and vice versa. So we refer to them collectively as sinusoids or sine waves. Here we go. Nice, smooth, and well behaved. No corners, no jagged edges. Uh-oh. How'd that get over here? I don't know. Well, we can fix it. So at 360 degrees, we're back at a maximum. There we go. Please raise your hand if you had this graph for cosine of x, y equals cosine of x. Nice job. Key starting point, 0, 1 for cosine versus 0, 0 for sine. And that's our major difference when we go to graph our parent functions at this stage. Awesome. The domain is the same for y equals sine of x and y equals cosine of x. Remember, the domain in general refers to the set of allowable x input values into my function. And it looks like these go on forever and ever to the left and to the right. So all real x's is the domain for each function. So all real x's. So all real x's are the inputs in each function. The range, however, is restricted, and so we see that only output y values in between -1 and +1 are produced. This is what we call a bounded function, where there's a maximum y value attained and a minimum y value attained, and the function is forever bounded between those. And so we could go ahead and write the range as -1 is less than or equal to y is less than or equal to +1. -1 is less than or equal to y is less than or equal to +1. And raise your hand if you have the domain and range correct. So you have the domain and range correct. Excellent. And then the period, right, refers to the length of time it takes to complete one full cycle in my function's behavior. So as I consider finding the period of one of these, I could grab onto any point in the function and then see how many units it takes to return to that same key point in its behavior. But I'm going to make it easy on myself. I'll grab maybe an easy to recognize point like this maximum on the cosine function. Everybody, let's take a look. How many x units does it take to complete one full cycle and return to the same key point, in this case maximum? Well, it takes, looks like it took 360 units to complete one full cycle. I didn't have to choose a maximum. I could have gone from minimum to minimum, or intercept to intercept, or any point on the graph. But the key is that you're seeing how long it takes to return to that same key feature in that function's behavior. So it looks to me like the period is 360 degrees for both the sine function and the cosine function. And why is that? Well, consider the model which we use to create our sine and cosine function parent graphs, right? We used a Ferris wheel model, and it took 360 degrees to complete one full rotation and return back to the same starting point. And so we could use a description here. We could say there are 360 degrees in one full circle in our wheel to get back to our starting point. Let's say 360 degrees in one full rotation of our circle. To get back to our starting point. We're just gonna make it. Just gonna make it. Awesome. What questions do you guys have about today's Bellwork? I'm going to go ahead and pause the recording here then, and after we do our homework check, we'll resume our recording. Okay, ladies and gentlemen, let's take a look at our content objectives. I'm super excited because today we're going to generate and develop the definition for a radian. This is a new way to measure angles. Okay, so just like we have different ways of measuring, let's say a quantity like length. In our homework, we've already had find the missing side lengths of the triangles, and we've had units from centimeters to miles to, I remember furlongs was even on a Bellwork question. So we've got all different kinds of units that measure the same thing, length. Well, so too do angle measures have different units we could use. You guys are familiar and comfortable with degrees, right? You're used to using degrees, but we can also measure rotations in different units, like revolutions, right? You look at your instruments in your car, and you've got your RPM, right? Rotations per minute measures the speed of your engine, right? Which with your crankshaft rotates in revolutions per minute. We've also got radians. Is going to be a way that we measure, almost used exclusively in calculus, because it makes an explicit connection between length, right? Straight line motion, and spin, angular motion. And so we're going to develop that connection today. A radian is going to be a bridge between angular motion, that is spinning motion, and straight line motion. Think about riding a bike, right? You could see how quickly your tires are spinning, right? How quickly your tires are spinning, that's angular motion, and translate that into straight line motion, right? The length of the trip from your house to the store, or something like that. And so the radian is going to be our bridge for that. By the end of today's class period, we'll be able to convert between degrees, radians, and revolutions, and those will be the three different units we'll be using to measure angles. Great. But before we do so, we're going to go ahead and remind you about, well, I don't want to call it your favorite class. Think back to geometry when you did your conversions, right? When you did your conversion. It was. Oh, I see that it was your favorite class for many of you. Nice. When you did your conversions, remember, we could start with one unit and end up with another unit, and so we need that to kick off the activity. The other thing is something you'll be doing first, and that's called drawing a turn arrow. So everybody, on the back of your Bellwork page, please, everyone find these quick 2 examples. We're going to complete these together and then begin the activity so that you guys have a common foundation. So number 1, we're going to draw a turn arrow. That shows the movement of the ray to another, and it indicates direction and stopping position. So everyone will be started with this initial side, OB, and we drew a turn arrow for 120 degrees. We'd say 120 degrees is rotating in the positive direction, so we go counterclockwise. We'd indicate direction with an arrow and stopping position. So we go right here. You'll draw the terminal ray. This would correspond to a turn arrow for 120 degrees. We showed the direction and the stopping position. That's why it's called a turn arrow. Make sure you do the arrow. Had this been negative 120 degrees, we still would have started here, but we would have drawn in the clockwise direction and put a little arrow after 120 degrees. The terminal side of our angle would have been in quadrant 3 somewhere. Okay. Awesome. The second thing before we can get going on our activity is reminding you about conversions. And so back to your favorite class, geometry, we could start out with your original unit and label, and we're going to multiply by an identity, a series of conversion fractions whose sole purpose is to get rid of the label we don't want, in this case inches, and end up with label the unit that we do want, in this case feet. So let's start out with the thing that we're given, 1,206 inches, label it with units, and then make it into a fraction over 1. We're going to go ahead and aim towards our goal unit. Our goal unit, we're moving towards feet. So I like to put that on the right side of the page. This is reminding me my goal at the end of the problem is to end up in feet. Now we'll go ahead and start at the beginning and multiply by an identity, a conversion fraction, whose sole purpose is to get rid of the label that we don't want and end up with the label that we do want. In this case, I want to get rid of inches. So in my conversion fraction, should I have inches on top or on bottom so that it cancels out? Austin? Bottom. So I'm going to have inches on the bottom of my identity. What corresponds to inches in terms of length? Keep in mind I'm moving towards feet. And so what identity will I use for my conversion fraction here? Cassie? In 1 foot, there's 12 inches. Thank you, Cassie. So now I see that I have inches on top, inches on bottom. I can cancel those out. It looks like I'm left with feet. If I wasn't, I'd go ahead and keep multiplying by a series of conversion fractions. Again, trying to get rid of the labels I don't want and end up with the ones I do. But it looks like I've done enough. And so we'll go ahead and go to our calculator. And I can go ahead and do multiply straight across, divide by each quantity on bottom. So I get 1,206 divided by 12. And I'm getting 100.5 feet. And we've already got our label in place. So 100.5 feet. Towards the end of today's activity, and when we come together for summary, right, we're going to go ahead and practice some conversions, but our units now aren't going to involve things like length, feet, and inches. They're going to involve angles, radians, degrees, and revolutions, and so that's where we're headed. Awesome. Okay, ladies and gentlemen. For number 5, you're going to select one representative from your group to come up and get a pipe cleaner. That pipe cleaner is going to be used in place of the string and tape that they suggest. However, there's not quite enough pipe cleaners, and so we're going to do one pipe cleaner per group. If they're all used up, then we'll go ahead and use string, but you don't have to tape anything down, all right? So we're also not going to cut, all right? We're not going to cut anything, and so you're going to use the same pipe cleaner, and you're going to measure off the different radius lengths in the circles using the pipe cleaner and make a mark on the pipe cleaner instead of cutting it. That way I can use them for my other classes. So please, no scissors today and no cutting. Everybody find the circles on the back of your handout. So activity number 2, flip to the back. In just a minute, when we break it into our groups, right, we want to make sure that each of these circles is taken by at least one group member. So on the back of activity 2, each person is going to be in charge of a different circle until they're all used up, and then before you get a repeat. So make sure that you at least do each circle once, and you'll be using your pipe cleaner to do that. Again, no cutting and no taping. You don't need to. You can use pipe cleaner or string, but just mark off the length of your radius when you get there, and that'll all make sense when you get to number 5. Stamped eligible items include 3A, 4B, 9C, 10B, 12D, and 14. I put those on the front whiteboard so you can see. In just a minute, I'll turn off the smartboard so we can save energy during our time, and we need about 15 minutes at the end. So we're going to be aiming for about 35 to come back together. Okay, so we'll have about 45 minutes to work together. You may select a reader or take turns. You want to make sure everybody's understanding, right? Before you guys raise your hand, I'll come together and I'll get you guys a stamp all at one time. I'm going to go ahead and pause the recording now. Thank you, ladies and gentlemen, for returning their desks to regular position. Let's go ahead and get started with our summary and then our closure. Okay, so this should work out perfectly. In our own words, let's explain how to draw a 1 radian angle. Okay, so how would we draw a 1 radian angle? Well, in the activity, we saw that the number of radius lengths that fit into the arc length determined by definition the number of radians that the central angle measures. So if we wanted to draw an angle that measured 1 radian, we simply draw an angle that intercepts an arc of 1 radius length. What? Well, if we took a circle, and we measured 1 radius length and took that radius length and wrapped it around the outside of my circle to get an arc that measures the same 1 radius length, and then connected that back to the center of my circle, we would have constructed by definition an angle that measures 1 radian. And so the number of radius lengths that fit into an arc length determine the number of radians that a central angle measures. And that will be key to our number of radians that exist in a 1 full circle rotation. But first, letter B, that's how do we determine the number of radians there are in an angle if you know the arc length formed by that angle? Well, that's kind of like the 16 centimeters. How many times did the radius length, 8 centimeters, fit into the arc length, 16 centimeters? Oh, twice, right? 16 divided by 8 gives me 2. The number of radians in that problem was 2 radians. And so what can we do to get the number of radians? Easy, we could go ahead and take the arc length, right? If we know the arc length, divided by our radius length. See how many times the radius length fits in to the arc length. That'll tell us the number of radians. So arc length divided by radius length equals the number of radians. Sweet. How many radians, exact and approximate, are in 360 degrees? And this was a big item of conversation as I walked in between the groups. This is a great problem and discussion. Sketch them all in the circle. So here we go. How many radians are in 360 degrees? We know that 360 degrees corresponds to 1 full rotation. 1 full rotation around my circle. In terms of length, right, one full arc around my circle corresponds to a length that's called its circumference. And the circumference C of a circle is given by 2 pi r, where r is the radius length. If I multiply radius length by 2 pi, I get the circumference C in my circle. Well, if the number of radius lengths that fit into arc length determine the number of radians in that amount of spin, then how many radius lengths fit into 1 circumference of arc length? 2 pi. 2 pi radius lengths fit into 1 circumference of arc length. Therefore, by definition, there must be 2 pi radians of spin in 1 full circle of rotation. So the number of radius lengths that fit into an arc length determine the number of radians. Therefore, there's exactly 2 pi radians in 1 full circle of rotation. Uh-oh. Rotation? No, rotation. Now we know that that's approximately 6.28, but we'll never use that decimal. We'll always use the exact 2 pi. Can I sketch them? Certainly. 1 radius length. 2 radius lengths. 3 radius lengths. A little bit more. 4 radius lengths. 5 radius lengths, 6 radius lengths and a little bit more. What do you mean a little bit more? You mean a little bit more, like 0.28 more? 6.28 approximately. There's 2 pi radius lengths in one full circle of rotation. Let's go ahead and practice converting. Again, we're using identities, and I'll go ahead and use the 2 pi radians for 360 degrees, or 1 revolution, just like you guys got your 14 stamp on. Here we go. Everybody, convert 128 degrees to revolutions. What you're going to have to do is your conversion worksheet, your day 7 conversion worksheet, backside of the lesson master, all that, 1 page, both sides of your homework assignment. Let's start out with the thing that we want to convert. In this case, 128 degrees. Make it a fraction by slapping it over 1. Multiply by a conversion fraction, an identity, whose sole purpose is to get rid of the thing we don't want and change it to the units we do want. We want to get rid of degrees. So just like before, we're going to put my unwanted label on the bottom so I can cancel them out. We wanted to move to revolutions, so I'm going to put revolutions, the label I do want on top. And now what's my identity? In 1 revolution, right, that corresponds to how many degrees? Lucas?
Oh, 360.
Absolutely. So I can go ahead and, what, it says show my work and reduce. So I'll go ahead and multiply straight across, divide by bottom, and then I'll math bracket. Everybody on your calculator, we can get our exact fractional answers by doing 128 divided by 360, enter, and then math, frac, enter. How sweet is that? So it looks like there's 16/45ths of a revolution in 128 degrees. So 16/45ths of a revolution. Awesome. Let's convert it to radians. So again, I'll start with my original. Slap it as a fraction over 1. Multiply by an identity. In this case, I want to get rid of degrees, but go to radians. So I'll put radians on top. What's my connection between radians and degrees? Well, based on our previous discussion, the number of radians that fit into 1 full circle is 2 pi radians. So that must correspond to 360 degrees. There's 2 pi radians in 360 degrees of rotation. Cancel out the label I don't want, degrees, end up with the label I do want. And guys, here's a neat trick. To get this exact, don't put pi in your calculator. Once you enter pi in your calculator, you make your entry irrational, and you'll never be able to math bracket and change it back into a fraction. So this is what we'll do. We'll divide by, or we'll leave our 2 pi out of it. So we'll go ahead and do 128 times just the 2 only. Everybody try it. Times just the 2 only, leave it out. Divide by 360, enter. Math, frac, enter, enter. And then we'll put the pi back in on top. 32 pi over 45. So there's 32 pi over 45 radians in 128 degrees. That's pretty sweet. In the interest of time, however, we've got to keep the party going. So let's go ahead and start with 4 radians. We're going to start with 4 radians, and we're going to convert to revolutions. Again, we make it a fraction. We multiply now by a conversion. What? I want to get rid of radians. So my conversion fraction, my identity will have radians on bottom so I can cancel it out. I'm going towards revolutions, so I better have that on top. What's my connection between revolutions and radians? Well, I hope we've seen that in 1 full revolution, there's 2 pi radians of rotation. Because there's 2 pi radians in 360 degrees of rotation, and that's equivalent to 1 revolution, so we've got our conversion. And this time they said nearest 100, and so that gives me the green light to enter in my calculator. Just make sure that you guys have parentheses around your 2 pi, otherwise you're only dividing by 2 and timesing by pi. We want to divide by 2 pi all on bottom. So I'm going to do 4 divided by 2 pi in parentheses. Close. 4 divided by, open parentheses, 2 pi, close parentheses. Voila! About 0.64, revolutions. Just to practice, we'll start at the beginning again, 4 radians to degrees. Slap as a fraction over 1. Multiply by a conversion. We're going to go ahead and get rid of radians. Go to degrees. So what's my conversion between degrees and radians? Go ahead and tell the class when I call on you. What's my identity? There's blank degrees and blank radians. What's my identity here? Nathan?
360 degrees and 2 pi radians.
Love it. Thank you very much. And if we're going to go to hundredths, then I can go ahead and enter the pi in there anyhow. Just make sure you put parentheses. That's perfect. Let's do it. 4 times 360 divided by parentheses 2 pi, close parentheses. Voila! Looks like we get about 229.18 degrees. About 229.18 degrees. Awesome. You guys are doing great. Think about the fraction we'd use to convert 3 pi over 8 radians to revolutions, right? 3 pi over 8 radians to revolutions to degrees. In each case, we'd start out with our 3 pi over 8. It's already a fraction, so I can leave it as a fraction. And we won't complete these in the interest of time because the bell's going to ring and we need our closure. I'm simply going to provide the conversion fraction. So to go to revolutions, we need revolutions on top. We need radians on bottom. In one revolution, there's 2 pi radians, Nathan tells us. Dot, dot, dot. That's my favorite problem. To go to degrees, I want degrees on top and radians on bottom. There's 360 degrees in 2 pi radians. Dot, dot, dot. Love it. Let's close it up. Starting your assignment. What is the connection between a radian and the radius of a circle? What identity should we multiply by when converting from degrees to radians versus degrees to revolutions versus revolutions to radians? Okay, what's the connection between a radian and the radius of a circle? Well, 1 radian of spin corresponds to 1 radius of length. So 1 radian of rotation corresponds exactly to 1 radius length on the outside of the circle. The number of radius lengths that fit into the arc length correspond exactly to the number of radians the central angle measures. How do I get from degrees to radians? This is for your homework assignment, backside of lesson master. To get from degrees to radians, I'm going to multiply by my identity, get rid of degrees, go to radians. Go ahead and tell the class how many radians are in how many degrees. What's my relation there? How many radians and how many degrees? Kelsey?
2 pi radians and 360 degrees.
Absolutely, thank you. There's 2 pi radians and 360 degrees. Next up, degrees to revolutions. Multiply by an identity. Going to revolutions, getting rid of degrees. What's my identity that relates revolutions and degrees? Eric?
2 pi. Oh, right. Oh, 1 and 3.
Good. In 1 revolution, there's 360 degrees. Perfect. You guys were 1 to go. You're doing great. To get from revolutions to radians, we'll multiply by an identity, a conversion fraction. We want to go 2 radians, so that's on top. We want to get rid of revolutions, so revolutions on bottom. Everybody, here we go. How many radians are in 1 revolution? What's my conversion here, Ian?
There's 2 pi radians to 1 revolution.
Absolutely. Great work, you guys. Keep in mind that your lesson master 10-9A and day 7 worksheets are the same thing. It's just 2-sided. So that one you picked up, guess what? No bookwork, ladies and gentlemen, no bookwork. I'll leave it up to closure to make sure I have the right answers, and I'll save the recording and post it to our Moodle site. Nice job today.